So we will move on. As I have told you in the first lecture, there are phases, equilibrium and phase diagrams. But to understand this phase diagram, we need to have basic knowledge of thermodynamics, because thermodynamics is a very basic thing for many of the engineering branches. So material science is not exception to that. Just let me just tell you a very nice cartoon which I found. This is a very nice picture. Two sills are moving in a ice water mixture in North Pole. As you see here, the first sill is telling the second one is telling the first one, hey, speed up in front, otherwise we are going to miss the class. The second guy, who is little bit of more engrossed in the atmosphere, he said, I know, but I am trying to figure out how we can describe these two phase one component system in terms of measurable parameters. So this guy is telling, what a geek you are already into the science, already into phase diagrams. So that is what I say, welcome to another glorious days of phase diagrams and phase equilibrium. So before I discuss, let me just tell you, in material science, thermodynamical description is basically based on Gibbs-P energy, and we know that Gibbs-P energy is given by G, capital G, by the names of Gibbs, who was a fascinating scientist, and G is defined like this. G is a function of temperature, is equal to H as a function of temperature minus T into S as a function of temperature. What is H? H is nothing but enthalpy. Okay. Enthalpy is nothing but heat content, some people say. What is heat content? Well, we know that the most important factor or parameter, rather not factor, in thermodynamics is known as heat capacity. So if you look at many thermodynamics books, even this one of these books which I referred in the first class, you will see that Cp is the prominent parameter determining almost all thermodynamical parameters like free energy, enthalpy, entropy, everything. So Cp is defined as a del Q by del T as a constant pressure, because there is another the heat capacity also at constant volume Cp, but in metallurgy and material science we use Cp. So enthalpy is can be written like this: at constant pressure dH by dt is equal to Cp. So therefore you can actually simply integrate it like this way, what I have written, dH equal to Cp dt. So therefore delta H is equal to integral Cp dt from temperature T1 to T2, very simple. And we can do this little bit expansion of delta H can be expanded and written like this, H2 minus H1. So therefore H2 is nothing but H1 plus integration Cp dt. So that means it boils down that enthalpy can be easily calculated by knowing the Cp of any material, Cp of iron, Cp of phase, any phase. If I know, I can calculate easily the enthalpy. So now what is St? St is, well, this is the general formulation before I go to the St. The Ht is nothing but H reference plus Ct. Reference is at a value of suppose certain temperatures, which is at 25 degrees Celsius and normal pressure. So now what is the entropy? Entropy is a thermodynamical parameter. I will discuss in detail what is its meaning, but let me just tell you what is the mathematical term. Again I can write down Cp equation. Cp is equal to del Q by del T, as you see here, Cp equal to del Q by dt at a constant pressure. So therefore I can write down del Q is Cp dt. Also second law of thermodynamics tells me that ds is equal to del Q by T. So therefore dq is nothing but T dds. Okay, I can write down this also here. For second law of thermodynamics tell ds equal to del Q by T reversible. So therefore I can write down del Q is equal to T ds, del Q is nothing but T ds. That is what I have done here. So you can clearly see I can get it like this, that the ds is equal to Cp by T dt. So if I integrate it, I can simply get delta S is equal to Cp by T dt integral over T1 to T2. So that is why we can easily get entropy So S1 equal to S2 equal to S1 plus this integral Cp by T dt. So by this you can simply calculate both the enthalpy and entropy of any system or any phase rather by using this formalism, provided you know the Cp values. Cp is the most critical intrinsic parameter used in the thermodynamics, and in a similar way St can be written as S reference plus T reference to T2 equal to G. Normally S reference is the given by the fourth law of thermodynamics, that is was entropy of a pure component at the absolute 0 is 0. So that is how actually we can actually get entropy. But remember, in thermodynamics we never ever use absolute values of enthalpy and entropy, we always use relative values of enthalpy and entropy, that is what is delta G. Now, so therefore G is as a function of temperature is nothing but H as a function of temperature minus T St. That is what I have given, and I told you that H is nothing but Cp T1 to T2 dt with plus H reference. Similarly this one T minus, I can write down S reference plus T1 to T2 Cp by T dt, right. So very easily I can calculate this. Now let me just erase this part because this requires me to use for the diagram. So I erase by keep only the del G equation there. So what you can see here, I plot G as a function of temperature as a constant atmospheric pressure, because most of our metallurgical system is actually constant. Let us suppose Cp is given by a simple function A plus Bt. Remember, I am just doing mathematical expressions. Cp is given by a simple function A plus Bt. A is a constant, B is a constant. So that means Cp is linearly related with temperature. So if I do that, I can actually create this curve which is nothing but enthalpy like this, this one you can clearly see. If I integrate that, it will become AT plus half Bt square plus H0 is nothing but H reference. So now simply I can do the enthalpy will be again A log T plus Bt plus H0 is the reference term. So by that I can calculate now minus Ts will be like this, because if you multiply it by minus T, this will be negative. So what is G then? G is nothing but H plus AT plus half Bt square minus H0 T minus AT log T minus Bt square. You multiply Ts, so Ts is this term, Ts is completely this term, okay. So G is this. Now how it will look like? How this will look like this is this curve, this is G, okay. So you can clearly see that I can get graphical representative of G as a function of time, temperature at a constant pressure. Okay, we will also vary pressure, but that we will see, I show you later, not now. So therefore, it is clear to you that we can calculate the most thermodynamic important function called Gibbs-free energy in a material science system very easily using this simple mathematical formalism. Those of you who have not this guide idea very well, you can refer to these books and understand it very clearly how actually the free energy things comes in the thermodynamics of phase diagrams and how it can be dealt with. But I have given you a fair idea about how to calculate and how to use it. Okay, now let us look at the examine the G for multiple phases, because finally we are going to deal with multiple phases like ice in water, or you are going to discuss like soap bubble, or you are going to discuss kerosene and water mixture, or you are going to discuss steels with a complex microstructure, right. So let us do that. Now I will plot here again G versus temperature. You can see temperature and G, temperature x axis G is and y axis at 1 atmospheric pressure. So this is what the black curve is basically tell you, G for one phase, because G will look like this a function of temperature. I have shown you earlier a sloping down curve, G for another phase. So this is one is known as G solid, but the black curve is for G solid. I write again G solid, and this red the pink curve is for G liquid, and they are actually making a crossover here. You can clearly see this is a crossover, and you know at this crossover the free energies of both the phases are equal, solid and liquid. Suppose water and ice, ice is what? Solid, water is liquid. So this the free energy of both of them will vary as a function of temperature like this. So this is the crossover point. Here dash correspond to the no difference between the free energies. Free energy of both the solid and liquid are equal. What is that called? That is what I have written, free energy of solid and liquid equal. That is what is the melting temperature of ice or freezing temperature of water, that is nothing but 0 degree Celsius. Okay. So obviously below this, below 0 degree Celsius or below the melting temperature of any component, okay, solid has a lower free energy than the liquid, and this is why solid is more stable. Ice is more stable than water at temperature less than 0 degree Celsius, because its free energy is lower than that. So therefore this is more stable, therefore this is the more equilibrium or the equilibrium phase, because energy is minimum. Now on the other side what happens? Gs is more than liquid, G liquid. So that means at temperature higher than this temperature, solid will not be stable, because solid has a higher energy than liquid, liquid will be stable. So that is why if you heat ice above 0 degree Celsius temperature, ice will melt to water. So you can clearly see how nicely thermodynamics can describe all kinds of phases and their transformations. That is the beauty of thermodynamics. So now one can actually do many things. The slope of this curve is what? Slope of this curve is nothing but entropy. So both of them can be written like this. So I have written this one, slope of solid curve and slope of liquid curves like this. They are actually entropies, entropy of solid, entropy of liquid. So let us consider, because G is an absolute thing, let us consider in terms of delta G, which is much easy to understand, much easy to do mathematics basically. So what we can do? We can do the same thing what I have done. I borrowed these curves again from the last slide, again free energy versus temperature, Gs and Gl, and delta G is then this one. As you clearly see, delta G is difference between the solid and liquid free energies. So delta G is 0 at the melting temperature. At 0 degree Celsius, ice, water, there is no difference of free energy between ice and water. Then as you go on this side, you can see here it is increasing, this left side also it is increasing. So you see here I have marked it like this, reference by a white arrow, okay, I get the point, I get another point, I get another point, okay, on the right side I get points like this, so I can calculate G. So what is the basic message you can get from this? Why do you have to use delta G versus temperature? This is a delta G versus temperature plot. Why it is more convenient? Because at temperature less than this equilibrium melting temperature, delta G is less than 0, okay, but above that delta G is more than 0. What does that mean? That means that for liquid to solid transformation, for liquid in water to ice transformation, delta G is less than 0 below the melting temperature. That means that liquid will easily solidify to solid, that means water easily freeze to ice at temperature less than this. But on the other hand, if the temperature is higher than 0 degree Celsius for ice water mixture, delta G is greater than 0. So the message is this, delta G tells you the spontaneity of the process. Whether a process will happen spontaneously or not depends on the sign of delta G. If the sign of delta G is negative for a particular process, then this process is spontaneous and will take place. If the sign of delta G is positive, process is not allowed. Thermodynamics calls this way whether a phase transformation or particular thing will happen or not. That is what is thermodynamics way of dealing with. So that is why from G I have moved into delta G, because delta G is easy to handle, and you know how delta G is given? Delta G is given by this equation. You can see here 8 zeros are your reference terms, minus AL, AS, AL is A for liquid, AS is A for solid, minus delta dash 0 time temperature, minus B terms temperature square half divided by 2, and then log term comes T log T. So by knowing all this A, B, C, or rather not B, C, A and B and delta A S0 and H0 and your HS H0L and H0S, we can calculate delta G. So that is very easy to do, very simple. Well, now I will just tell you what is the difference between a mechanical mixture and a chemically homogeneous mixture. Like if I put sand and salt together, it is a mechanical mixture, they do not mix each other. But if I put salt in water, completely get mixed each other. Let me just explain it. Suppose, and there only I can bring about the basic concentration terms very easily. Till now we are discussing about only temperature, G as a function of temperature, G as a function of temperature at constant pressure, that is what we discussed. Let us now discuss a function of composition. So suppose I have A and B. Let us assume A is sand, as A is salt and B is water. So I have X as the fraction of water and 1 by X is a fraction of salt. Okay, I put them together. If they are not mixing together, they are mechanically mixture, like they are not mixing together means they are not getting intermixed. I will get P energy versus concentration or X, this is X, like this line, because this is nothing but what? G is nothing but, okay, let me check this thing, okay, black, okay, G is of the mixture is what? This is nothing but 1 minus X G of A plus X G of B, and this is a straight line equation, clearly see that. How it is? 1 GA plus X GB minus GA, okay, that is what. So this is X, this is a straight line equation and I have plotted that. Now forget about this term mu A0, mu H, mu B0, and you can clearly see P energy of this composition, which is 1 minus X and X, is given by this point, because I can, this is 1 minus X, this is X, very simple, got it. Now these are the points which is written mu A0 and mu B0, which I will discuss in future slides. You know, before I go back into P energy terms, I just want to tell you entropy, which is a very important thing in this description, was first time discovered by Boltzmann, all of you should know that. And in Boltzmann tombstone, his equation is written, you see here S, K, L and W, very important equation, because he only first time described this equation and gave us a new path. But unfortunately, nobody believed him in those days, so he has to commit suicide, or rather he committed suicide. And this is a very fascinating story, that how such a brilliant person was ridiculed in those days for one equation, and he did not have any choice. So now if I take a solution instead of a mechanical mixture, in a mechanical mixture P energy of the system is nothing but a linear relationship as a function of composition. But suppose if I take a solution, like I told you salt and water, that is what I have taken the example, salt and water, A salt, B is water, and I put it together, they will mix nicely, okay, you know that the atomically mixing is possible. For that the P energy will be given by this curve, the one which I have drawn like this, not the straight line. Why? Because of Boltzmann, that I am going to discuss now. Boltzmann only gave this equation, that is why it is possible. So for a physical mixture, this is what the straight line will give, for a alloy or for a solution rather, this will be the P energy curve. P energy will be like an inverted parabola, and for any composition P energy can be given. So what you understand from this picture, before I tell you why this shape is like this, is that if I have a physical mixture, P energy is given by this red thing, and if I have an alloy of same composition, it will be given by this one. So basically the energy of the alloy, P energy of the alloy is lower than the P energy of physical mixture. That is why if I add salt into water, it has to mix, because energy will be lowered. Instead of, if they are remaining separate, energy will be higher. So better the salt get mixed into water. That is why salt easily gets mixed into water, sugar easily gets mixed into water, coffee easily gets mixed into the milk. That is the reason, because solution and energy of solution is lower than the energy of the physical mixture, and difference is quite large. You see delta Gm is the difference is very large. So now why do you get that? Okay, this is mainly because G is nothing but H minus Ts, and S term, that is what is brings down this free energy curve. What is S? S is the entropy, and as Boltzmann has given S nothing but K ln W. And those of you who know a little bit of this one, okay, basically this term for a solution can be written like this. Solution, it will be S of solution is equal to S0 plus delta S, S0 plus delta S is nothing but R, this is minus, sorry, R x ln x plus 1 minus x ln 1 minus x. Okay, this any undergraduate book will give you this expression. This expression can be easily obtained from this Boltzmann's equation. So therefore, if I plug in this S there, and we know enthalpy can be calculated by using Cp values, so we will get a expression like this. Okay, even if enthalpy is very not dependent on much dependent on composition, still you will get this equation, because x ln x or 1 minus x ln x 1 minus x is nothing but a equation of a parabola, and you get a negative parabola because there is a negative sign. That is why you get this. Now G of at any composition is given by this, where x is this is easily obtainable, and here mu a0 and mu b zeros are the free energies at the pure component, like pure A will have a free energy of mu a0, pure B have a free energy of mu b0. That is why these are actually called mu terms. And in fact, you can easily draw a straight line tangent, not a straight tangent at this point, and get the free energy or a chemical mu at this point A and at pure B like this. So therefore, G is nothing but 1 minus x mu A and x mu B. Clearly you can see why, because this is a straight line has this part and this part, so summation of that is nothing but a free energy of x. That is why. So this is what is known as tangent to curve rule. Okay, we will move forward further how to use this concept in the next class. So let me just tell you that G is as a function of temperature and as a function of composition. I have described you and told you, and in this lecture you should refresh your minds and using literature, internet or books, and we will go forward for the further.